Hi, welcome to the Aerospace Maker channel. I'm Aaron Harper. This channel is all about the nuts and bolts of aerospace. This week is a propagation segment of the link budget in preparation for a satellite reception project. At the end of these videos, we'll have made a satellite ground station receiver and received images from space. This week we'll cover the communications link from the spacecraft antenna all the way to the ground station receiving antenna. If you've not seen this series' previous videos, I encourage you to view them to see how we arrived at these figures rather than take our word for it. There's also going to be a fair bit of math in this video, so have a decent scientific calculator handy. I personally use RealCalc on my phone. It reminds me a lot of a Casio calculator that got me through college. So I highly recommend it. It's available for Android. Should you get lost, like I said, there's a lot of math. So if you get lost, don't panic. That's why it's on a video. Just rewind and have a look again. Also, use our website. The step-by-step math is going to be posted on the website, and pretty much the entire narrative will be posted there as well. So, feel free to use it. It's what it's there for. It's on our website, aerospacemaker.org. Bit of a review of the previous videos, a little recap. Our scenario is to receive the images from the NOAA 19 weather satellite. And we're assuming that our satellite is 60 degrees above the horizon at an altitude of 870 kilometers above sea level. And it transmits at a frequency of 137.1 megahertz, 137.1. We also know that the satellite's output power, as we calculated it in a previous video, is positive 12.45 dBW as an estimated isotropic radiated power, or EIRP. Again, 12.45 dBW. Now, let's break it down a little further rather than try to step through this whole thing in one shot. There are several calculations we need to do in order to figure out the signal, what kind of signal we'll receive at the ground station. So the first step will be to figure out the distance between the satellite and the ground station. That's called the slant range. Now this will require a bit of trig, but don't worry, we'll step through it bit by bit. With a slant range, we can figure out the free space propagation loss. That's the loss where any signal or any energy radiates in all directions and thus is diminished over distance. And we, while we are a small part of that sphere, and therefore we receive a smaller part. The further away it is, the less we receive. This is also known as the inverse square law. An example of this would be a flashlight would probably blind you looking straight at it at arm's length, but if you put it on a mountaintop several kilometers away, you might not even see it. It will be very, very dim, and the further out you go, the less light will actually hit your retina, which you are interpreting as light. The third step is we need to figure out how much of the slant range is in the atmosphere. You see, the atmosphere absorbs a certain amount of spectrum of light, but it also absorbs and refracts a certain amount of the radio spectrum. We need to figure out what frequencies are affected, how they are affected, and derive how much of that slant range, the distance from the ground station to the satellite, is in the atmosphere and thus affected by the atmosphere. Finally, we need to add all those things up, all those losses, and take that 12.45 dBW signal, apply those losses, and see what we get at the other end. Now, to understand the issue, let's look at this illustration and review what we know and what we need to figure out. The satellite, the ground station, and the center of the Earth make up a triangle that we can solve for all angles and sides using a bit of trigonometry. We need to know the distance between the satellite and the ground station, which is labeled D in the illustration. We know the observation angle is 60 degrees above the local horizon, and the altitude of NOAA 19 is 870 kilometers above sea level. Now let's start with the ground station elevation angle. Labeled with the Greek letter theta in the illustration, we know that this angle is 60 degrees above the local horizon. And we also know that the local horizon is at a right angle to the center of the Earth. Now that puts the angle E in the lower portion of the image at 60 degrees plus 90 degrees, or a total of 150 degrees. So E is equal to 150 degrees. We also know that a distance to the center of the Earth from sea level, RE and RS in the illustration, that number is 6,378 kilometers. Now NOAA 19 is at an altitude of 870 kilometers, so therefore the distance from the satellite to the center of the Earth, Z in the illustration, is 870 plus 63,078, or a total of 7,248 kilometers. That is 7,248 kilometers. Now, for simplicity, let's just say the ground station is at sea level, and we use RE, or radius of the Earth, equal to 6,378 kilometers. Now, if it weren't, we would just simply add the altitude of the ground station above sea level to the radius of the Earth, just as we did with the satellite altitude. I, for example, am at about 2,500 meters, 2.5 kilometers above sea level, so therefore my altitude, or my RS, plus altitude, or the distance from me to the center of the Earth, is 6,380.5 kilometers. But just for simplicity's sake, let's just use 6,378 as the ground station altitude above the center of the Earth, which puts it directly at sea level. Now, at present, we can't quite get the slant range with the data we have, but we can calculate the rest, since we have one angle, E, the opposite side, Z, and at least one other side or angle, which is RE, or the radius of the Earth. In order to calculate the rest, we need to use something called the law of sines. Now, the law of sines states that the sine of an angle over the length of the opposite side is equal to the sine of any other angle over its opposite side. Given this triangle, the sine of the angle A over the length of segment A is equal to the sine of angle B over the length of the segment B is also equal to the sine of angle C over the length of segment C. You'll notice that the angles are capitalized while the segments are in lowercase letter, just to aid a little clarity there. Now, with this handy equation, we can solve most triangles broken down into segments and angles where the angle and opposing side is known, just any of them. As long as one angle and its opposing side is known, we can get there. This establishes a ratio, and with this and one other piece of information, an additional side, an additional angle, we can figure out the other side, or the other angle. And from that, as you'll see, we can gather the rest. Now, since we know both the values of the angle E of 150 degrees and segment Z, which is 7,248 kilometers, we have a ratio. We also have the length of the side RE, which is the ground station altitude above the center of the Earth, which is 6,378 kilometers. And with that ratio of the sine of E over Z and RE for the radius of Earth, we can figure out the angle S, which is the look-down angle of the satellite. Now, substituting some values and moving some terms around, we get this. The sine of S over 6,378 is equal to the sine of 150 over 7,248. What we have here is the sine of S, which is our look-down angle, over 6378, which is the RE figure, the altitude of our ground station above the center of the Earth, equals the sine of 150, which is our angle from the center of the Earth to the satellite, over 7248, which is the altitude of the satellite over the center of the Earth. Now, if we run the numbers, we find that the sine of 150 is 1/2. So therefore, let's throw that up there real quick. Sine of S over 6378 is equal to 0.5 over 7,248. Well, that's not so bad. So let's take it one step further. Let's reduce this into something we can read. And we can do that simply by doubling both terms. So, the sine of S over 6378 equals 1 over 1,400 and 14,496. But we still have got that odd term here. So let's move it around a little bit. The next thing we can do is we can multiply both sides. So therefore, the sine of S equals 6378 over 14,496. What I've done is I've basically multiplied both sides by 6,378. We still have got this sign here. Well, what we do is we use the sign to the negative first power on the opposite side. We basically cancel it out by doing it both. Sine to negative 1, sine S, sine to negative 1, and this means that it reduces down to only S equals and then the rest. So let me demonstrate. S equals the sine negative 1 6,378 over 14,496. Close parentheses. Now the next step is to solve something. Let's solve our real numbers there. S equals sine negative 1, and that comes to, and I'll put it in parentheses to make it clear, 0.44. Now that's a fairly accurate approximation, but we'll just call it close enough. Now, using a calculator to solve this portion of it, we discover something. S equals 26.103. Well, that's our look down angle actually. Our look down angle is 26.103 degrees. The next part is a little more difficult. We've solved two angles and two sides, but we still don't have what we need to figure out the slant range. But the next part is easy. We know that the sum of all the angles in a triangle must equal 180 degrees. Therefore, since we already know that angle E is 150 degrees, and the angle that we just figured out, the look down angle, is 26.103 degrees, we can simply subtract from 180 degrees 150 degrees, which leaves us 30 degrees, and then subtract 26.103 from 30, which gives us 3.897 degrees. That's our next angle, 3.897 degrees. That's the angle between the center of the Earth, where we are at the ground station, to where the satellite is above the Earth. It is the angle right at the center of the Earth. Now, all we have to do now is use, again, the law of sines to solve for that slant range. So basically this is lather, rinse, repeat. Now from that first law of sines equation, we already have a ratio of 0.5. From here, we understand that it's 0.5 over 7,248, which is actually 1 over 14496, 14,496. So we already have the first portion of that. So let's just solve it. We're solving for D, the length D, which is our slant range. So the sine of the angle, which we already know is 3 point, what did I say it was? Yeah, 3.897 degrees over D is equal to 1 over 14,496. That's not hard. So let's take it to the next step. From there, we can say that since we can multiply this out, we can say that D is equal to the sine of 3.897 times 14,496. So at that point in time, we can solve that problem the same way, and then we discover that D is equal to 985.192. Our slant range, the distance from the ground station to our satellite, is 985.192 kilometers. This is great. This tells us the distance that we need to know. But what it doesn't do is it doesn't tell us how much signal we have lost. Well, the formula in order to figure this out The free space propagation loss formula is (20) times log 10 of the distance plus 20 times log 10 of the frequency plus a correction factor of 32.45. Now this correction factor is to make sure that units are understood. This correction factor varies if we wanted to use different numbers, but our distance is in kilometers, our frequency is in megahertz, and our output that we expect is in decibels. So this yields the free space propagation loss that we want. So let's plug in some real numbers. At this point in time, free space propagation loss is equal to 20 times log 10 of 985.192 plus 20 log 10 of 137.1 plus 32.45. Now this is where a good calculator will come in handy, because you just basically plug the number, get the log 10 of 985.192, multiply it by 20, and do it with each term. So let me restate that using the numbers that we get from the calculator. Our free space propagation loss is equal to 59.87 plus 42.74 plus 32.45. So all we have to do now is add it. And it all comes out to our free space propagation loss is equal to 135.06. And we'll come back to this guy here in a minute. But what that means is we lose 135.06 decibels of our signal before it even gets to the ground station. The only thing left to calculate is how our signal is blocked by our atmosphere. There's a lot of models for how the atmosphere absorbs signals, and to an extent they're all right and all wrong. We all know that the weather is kind of unpredictable. It's kind of like the science of weather predicting. Sure, there's a science to it, and sure we can do that, but occasionally Mother Nature gives us a little bit of a surprise. The complex real world does not follow a simple math function, and weather and other less visible atmospheric phenomena can and will change the values. In my opinion, until we figure out all the variables in order to figure out what kind of effect the thing has, something simple is easier because it yields a similarly accurate result without a whole bunch of work. So let's just use a simple model as a guideline and we'll work from there. That brings us to the chart. In this chart, we can see the signal attenuation of the primary factors in our atmosphere, which is water and oxygen. The water is in the form of water vapor. Now in our chart on the x-axis is the frequency in gigahertz, and the y-axis is the attenuation of the signal, in other words the signal loss, in decibels per kilometer of atmosphere we have to go through. Now unfortunately this particular chart is in gigahertz. So if we look at 137 megahertz, it's actually off the chart to the left. Now we find that the effect of water vapor is below the measurable limits. That kind of peters out somewhere around, looks like 1, 2, 3, looks like about 4 gigahertz. Is, might as well not even worry about it. But the oxygen, on the other hand, which is the red line here, continues on almost flat line through the end of the chart. Now if we kind of project over that way, the effect of oxygen on our signal could be projected at 0.005 decibels per kilometer of signal attenuation. Again, this is an approximation, but it's close enough. Now, the atmosphere does not go all the way to our satellite. So we need to figure out how many kilometers of atmosphere we're passing through. The truth of the matter is that our atmosphere does go all the way out there. It's just not at any density that really has any effect on either the drag on the spacecraft, doesn't give it aerodynamic lift, and it also doesn't attenuate the signal. And the point at which, the arbitrary point that we decided it no longer applies, is called the Kármán line. The Kármán line is 100 kilometers above the surface of the Earth, above sea level. And therefore, that is our real world answer that we'll use. Again, simplicity over complexity, and just about as accurate. Now, we know that NOAA 19 is at an altitude of 870 kilometers. And we know that the slant range is 985.192 kilometers, and we can use this ratio, the ratio between these two numbers, to determine the amount of the slant range that is below the 100 kilometer Kármán line. Let's step through that. We have our slant range of 985.192 kilometers. So 985.192, and we know that the vertical, the altitude that NOAA 19 is orbiting is 870. So let's make that a ratio over 870. Then once we have a solution here, what we need to do is we need to multiply that by 100 to get the amount of the slant range that is below the Kármán line. So let's put times 100. Now what we can do is, this is greater than that, so this is going to be 1 point something. And sure enough, it passes the sanity check, because what we get here is 1.1324, and we multiply this by 100, and we get 113.24 kilometers. This is the amount of atmosphere that we're going through below the Kármán line. The next step is to take our atmospheric loss that we saw on the chart and multiply it by the distance. So we have 113.24 times 0.0, how many zeros were there? 0.005. All right. Now, this simple problem comes out to 0.566 dB. Okay, so here is our atmospheric signal loss. Here's our free space propagation loss. And by the way, both of these are negative numbers. So, we need to go back to how strong of a signal we started out with, which was the 12.45 dBW, or decibels per watt. Let's take it up there. It is 12 point, I'm going to make sure I get this right, 45 decibels per watt, that's a positive number, minus 135.06 minus 0.566. You'll note that these are decibels, and this is dBW. Fortunately, the reason that we use decibels and decibels per watt is that they, for all intents and purposes, interchange. It allows us to go through it and simplify the process down to basic addition and subtraction most people can do to some degree in their head. So let's go ahead and solve this one. This comes to 123.176. So our signal strength is 123.176 dBW at the ground station antenna. Now, we've got a fair amount of signal to make up over there, but fortunately we should have the equipment to pull it off. Well, that's it for the transmit section. Next week we'll go through the receiver segment for NOAA 19. The equipment we hope to use is an inexpensive software-defined radio receiver called the RTL2832U. These radio receivers, this is a chip that is generally integrated into a little dongle that plugs into your USB port on a computer. It was originally designed to pick up television broadcasts, and then some very smart people figured out that you could use it to pick up all kinds of things because it had an incredible range of frequencies that it could grab. Oddly enough, you'd think something like this would be a fairly high dollar item. They can be had in online vendors, including Amazon, directly from the manufacturer, any number of direct from the Orient shippers. Generally speaking, they're about $10 or $11 US. And like I said, they connect to any modern computer's USB port. It needs to have a USB 2 or USB 3 port. The original USB version 1 that was used, like, say, around a computer that's 15 years old or more, it just simply won't have the bandwidth to be able to pull the signal through in the digital form. Now, if you want to get a jump on things, go ahead and order one online. The software to run this device is generally free. There are some ones that you can pay for, but I highly recommend getting the free ones, one thing free. And I highly recommend you have a look at some of the open source versions. GNU Radio, if you're into using building blocks to construct radio receivers, you can do it on the command line if you're a purist. I am not. GRC, which is the GNU Radio Companion, allows you to build radio things of all kinds, not just radio receivers, but transmitters, radar sets, differential receivers, you name it, you can do it. and does it by essentially connecting blocks. It's a very neat thing. It is certainly worth your time to explore. But the software that I generally use for satellite reception, because I want to focus on the reception, not necessarily on the science of getting there, is GQRX. It's not only is it free, it is also open source, which basically means you can go in and have a look at the code to understand how it works. Now, if you do order one, you probably want to look for one that has an R820T tuner. This is generally what I will use because I happen to have a few of them. I bought, I think, 10 or 12 of the things to play around with. There's a new one that uses an R820T2 tuner, which is superior in every way and completely compatible. If you have a choice between the R820T and the R820T2, don't even think about it. Just get the R820T2. It is quite literally superior in every way, and it's almost the same price. Get that one, and it usually comes in a blue case instead of a black one, like what you'll see me use. So that's pretty much it for this one, and as always, let's go. Please like this video if you like the channel, and subscribe to the channel so you don't miss a video. Visit our site, aerospacemaker.org. As time goes on, more and more information will be presented there. To support this channel and accelerate improvements, please donate to us through the Patreon link below.